Hello everyone, welcome to this lecture. We'll continue with our fourth module, that is use of free energy in calculus program. Myself Dr. Ranjana, and we have discussed all these topics, that is thermodynamic function, energy, entropy, free energy, okay? Then estimation of entropy, free energy, estimation of free energy and EMF, cell potential, right? The Nernst equation and its application, general concept of acid base, oxidation reduction, and solubility equilibria. These all parts we have discussed earlier. Then today we will discuss this one, that is use of free energy consideration in metallurgy through Ellingham diagram. Right? We'll discuss today. Okay. This one is Ellingham diagram. This diagram, this graph, this plot is known as Ellingham diagram, and we'll discuss what is this and use of free energy consideration in metallurgy through Ellingham diagram, right? This is a plot, or you can say it is a graph, that is called Ellingham diagram. And now come to point that what is Ellingham diagram, right? And we have to know about use of free energy consideration in metallurgy through Ellingham diagram. Okay, what is it? This Ellingham diagram is a graph showing the temperature versus standard free energy of a reaction involved in extraction of metal from its respective ore, right? What is it? This one, this Ellingham diagram is graph showing temperature versus del G. Okay, this one is del G naught, that is standard free energy change, and at this axis temperature in centigrade is present. Okay, and it is a graph showing temperature versus standard free energy of a reaction involved in extraction of metal. These are the plot for reaction involving extraction of metal from its ore. As we know, metals are extracted from its ore, right? And generally oxide or sulfide ores are present for metal, and by reduction of oxide or sulfide, this extraction of metal express or metal can be reduced from its oxide ore generally. Okay, and we can plot this Ellingham diagram for oxide or sulfide ores for any metal. Okay, different types of metal. Okay, this type of diagram are very much useful in predicting the feasibility of thermal reduction of an ore. It is important for predicting feasibility of thermal reduction of the ore and to select the appropriate reducing agent in the reduction of oxide or sulfide ore. This diagram were first constructed by Ellingham, that is scientist Harold Ellingham, right? And it is very much useful for metallurgical process, as we know that del G naught, that is free energy, standard free energy change, is equal to minus RT ln K. Okay, this is the equation for del G naught, right? And del G naught will be is equal to del H naught minus, that is standard enthalpy change, minus T delta S naught. That this one is change in entropy at standard condition. It is, this equation is known for you, that is del G naught will be is equal to del H naught minus T delta S naught. And for spontaneous process, we know that any process will be spontaneous, any reaction is possible only when del G should be negative for that process. Okay, negative value of del G is required for any spontaneous process. Okay, in this equation, this del H is enthalpy, this T is temperature, del S is entropy change. Okay, and this diagram is based on this equation. Okay, Ellingham plotted a experimentally determined standard free energy, that is del G naught, for various oxides using 1 mole, only 1 mole of oxygen with temperature at partial pressure 1 atmosphere. Right? Ellingham plotted the graph between del G naught and temperature, del G naught of various oxide using 1 mole of oxygen. Is the formation reaction of oxide using only 1 mole of oxygen, and partial pressure is 1 atmosphere for oxygen, and this is the reaction of the formation of the oxide, and the del G naught of these reaction for different metal reaction, this del G naught is plotted against temperature in this Ellingham diagram. You can see that these are the temperature. At this axis temperature is present, at this axis del G naught is present. Okay, and if you observe, this all values are for del G naught is negative, positive values are not there, right? This one is 0, minus 200, minus 400, minus 600, minus 800, and so on. These all lines are present below this 0 value, because above 0 value del G naught will be positive, and for that positive del G, any reaction is not possible. For any reaction, positive del G means reaction can't be possible. Reaction is impossible. Okay, for any reaction, this del G should be negative. Okay, these are the negative value of the del G. Okay, and at this axis, temperature is present. Now, Ellingham find out that del H and del S, in this equation del H and del S, right, of the formation of compound do not change significantly with temperature as long as state of product or reactant remain unchanged. If state of product or reactant will change, that is solid to liquid, liquid to gas, then only this del H or del S will depend upon temperature. Otherwise, he found that this del H naught, that is standard enthalpy and standard entropy change of formation, do not change significantly with temperature. Okay. General form of del G versus T plot gives straight line with positive slope. You can see that all these lines in this diagram is a straight line with positive slope. Slope is positive, it means towards the upward direction. Okay, except these two lines, this line, red line and blue line. All lines have positive slope, right? That is general form of del G versus T plot gives straight line with positive slope. This one is your reaction, your equation, that is del G naught del H naught minus T del S. Okay. If you compare it with a straight line equation, that is del G naught will be A plus BT. Okay. This A can be considered as del H naught and B, that is slope, considered as minus del S. That is, for that equation, for that plot, if you plot del G versus T, then it will be straight line and slope will be considered as minus del S, and this one, that is intercept, will be del H, right? For this reaction, if you plot this one, del G naught versus T, then this will be minus del S, will be slope, and this will be intercept in this diagram. This one is intercept. For example, for this line, this one is del H, this one is slope, is minus del S. Okay. These straight lines in diagram shows the relative stability of oxide. You can observe this is the lines for calcium oxide formation. This one is line for magnesium oxide formation. These all lines for different oxide formation. These are the plot for experimentally determined del G naught for this reaction, this formation of oxide reaction versus T. Okay, this one is line for aluminum oxide, that is Al2O3 formation. This is for TiO2 formation. This is for SiO2 formation. This one for MnO. This one for Cr2O3. This one for zinc oxide, and this one for ferric FeO, this one for Fe3O4, this one for NiO, that is nickel oxide, and this one for copper oxide, and all that. These all are different lines for formation of different oxide. Okay, and these straight line in the diagram shows that relative stability of oxide. What does it mean? The relative position of lines in diagram can give idea about affinity of metal with oxygen. That is, more position of any lines in this plot will give idea about stability of that oxide. That is, more affinity with oxygen, it means more stable oxide formation. Okay, the stability of particular oxide can predict by just observing these lines in diagram. Just comparing these lines after you can compare the stability of each oxide. Lower the position of line, greater the stability. It means this MgO is more stable than aluminum oxide. This aluminum oxide is more stable than TiO2. This one is more stable than these all oxide. Okay. Lower the position of line in the diagram, greater the stability of oxide, right? It means easily reducible oxide will be present at higher position, and more difficult to reduce oxide will be present at the lower position. Most stable oxide will be present at lowest position, and most unstable oxides will be present at a higher position, that is Au, Ag, Hg will be present in that position. Okay, and these are this calcium oxide, magnesium oxide, aluminium. These are the lower in position in this diagram, and these are the oxides which are difficult to reduce. These oxides are most stable oxides. Okay, and these are the oxide having good stability, which occupy the position in middle portion. Okay, this one is most vulnerable area, that is most unstable oxide lines present in this area, and in this area most stable oxides are present, and in this area oxides are present which have good stability. Okay, a given metal can reduce the oxide of all other metal whose lines present above its line. What does it mean? It means if you consider this line, that is a line for aluminium. This is the aluminium, formation of aluminium oxide. This line shows the formation of aluminium oxide, and this aluminium can reduce the metal, can reduce the oxides of all the metal whose lines present above this aluminium. Okay, it can reduce this TiO2, SiO2, MnO, Cr2O3 and all that. Okay, a given metal, if you consider this one, it can reduce SiO2, MnO, this Cr2O7, ZnO, Fe2O3 and all that. But this TiO2 can't reduce aluminium, okay, or magnesium or calcium. Okay, for example, this magnesium line lies below this TiO2, and this magnesium can reduce this TiO2, right? If you use this magnesium as a reducing agent, then this magnesium can form magnesium oxide easily in presence of TiO2, and this TiO2 can convert into Ti by reduction caused by this magnesium. Okay, it can be acts as a reducing agent for this ore, that is TiO2. Then next point is that the greater the gap between any two lines, the greater the effectiveness of reducing agent corresponding to the lower line. Right? What does it mean? Greater the gap will be there, more efficiently lower metal can be used more efficiently as a reducing agent. For example, if you use this aluminium can be used as reducing agent for this manganese, right? But this TiO2 can also reduce this manganese, but the difference between these two lines is less than these two lines, and aluminium is more efficient reducing agent for this magnesium oxide than titanium. Okay, understand? And these points shows that phase change. At that point, slope increase or may decrease. Okay, this is the M, that is melting point, shows melting point. This one is boiling point. For example, this MgO, this one is melting point, this one is boiling point. For aluminium oxide, this one is melting point, this one is aluminium to Al2-3, and this one is melting point for this line, this one is melting point for this line, this one is melting point for this line. These are the melting points for any oxides, okay, which can show the deviation in the slope. Okay, this is the deviation in the slope in each line. Otherwise, it will give a straight line. Okay. The distance between two lines at any temperature, represent the standard free energy change accompanying the reduction at that temperature. If you want to compare these both line, you have to consider it at any temperature. You can observe it for a particular temperature is the difference between them at this temperature. This one is difference between these two lines at this temperature. You can predict temperature for reduction also by this type of diagram. For example, the reduction of chromium oxide by aluminium at 1200 degrees centigrade. Okay, if you consider it, this aluminium can act as a reducing agent, right? And this can convert this chromium oxide to chromium by converting itself into aluminum oxide, because aluminum oxide is more stable than the chromium oxide. Okay, you can compare it in this diagram. This is the line for aluminum oxide, this one is line for chromium oxide. It is more stable oxide than chromium oxide, and aluminum can convert this chromium oxide into chromium metal. And if you observe it at the 1200 centigrade, this is the 1200 centigrade, you should compare. If you want compare it at the particular temperature, then you will get this one is the difference between them at this temperature. Okay, the temperature is also important. But this aluminum can act as a reducing agent for chromate, that is oxide of chromium, but this nickel oxide can't be used as a reducing agent because it is less stable than the oxide of chromium. This oxide can be reduced in the presence of aluminum but not in the presence of nickel. Okay. Then slope of curve is represented by minus del S0. And what is del S? That is change in entropy. That is summation of entropy, standard entropy of product, summation of standard entropy of reactant. Okay. For this general reaction in which metal form oxide, this one is solid form, metal is solid state, this oxygen is gaseous form, and this formed oxide will be always solid. Okay, then entropy of solid will be always greater than gas. The entropy of whole reactant will be always higher than solid, that is product. So this one, that is del S, will be always negative, and in this Ellingham diagram all slopes having positive slopes, right? It means solid minus this metal, this oxygen will be always negative, and the slope of most of curve is positive. As you can see that these are all positive slope because this negative del S value is positive in all cases. Okay, except two, that is blue line and red line. Red line is for formation of CO, that is carbon monoxide. This is the for formation of CO2, that is carbon dioxide. Why these lines are exception? This CO and CO line, this is the reaction for CO2 formation, carbon, O2 and CO2. This one is solid, this one is gas, this product is gas. It means change in this entropy between product and, that is 1 mole of oxygen, 1 mole of the carbon dioxide is produced, and the change in entropy is almost zero. Okay, thus the line is horizontal in case of CO2 formation. That is, this line is horizontal because del S is almost zero for this case, and line is horizontal, slope will be zero. Okay, and for this reaction, that is formation of CO, this is the carbon O2, 1 mole of 2 can form 2 mole of CO. It means product have higher entropy than the entropy of reactant, and del S is positive in this case, and this diagram is for negative del S slope. So this line of CO is having negative slope in this diagram, and as lines of CO interact the lines of most of the metal, right? This CO line intersect the lines of most lines in this diagram. So this carbon can considered as very good reducing agent at higher temperature. It means at higher temperature above 1200 or 600, this line is here, and if you compare the stability of this CO at this temperature, then these all metal can be reduced in the presence of carbon, and is very much important because carbon, that is coke, is very easily available and a cheap reducing agent, right? And these two lines, that is lines of CO2 and lines of CO, intersect each other at 700 degrees centigrade. So this CO is more stable than CO2 at the temperature higher than 700 centigrade. Above this temperature, it will be different. This will be more stable than CO2. Then reduction of refractive oxide, that is TiO2, MgOs, L2O3 by carbon is difficult due to requirement of very high temperature. Reduction of these metals are difficult because it requires temperature higher than 2000 degrees Celsius. Okay, if slope increases, its slope will increases, then the reactant changes state with the temperature. If slope decreases, then reactant change, product change with state with temperature. Okay, this carbon can reduce chromium, SiO2, TiO2 above this 1200 degrees centigrade. Above this 1200, it can reduce these all oxides. Okay. Then come to application of Ellingham diagram. It helps to predict feasibility of thermal reaction of an ore, that is metal oxide, and it helps in deciding the temperature for reduction. Okay. It also helps in proper choice of suitable reducing agent and the reduction of oxide ore. Normally, coke can be used as reducing agent for all metal oxide because it is very much cheap and easily available. Okay, at high temperature, it is the best choice for reducing agent. Then you can see some examples, that is reduction of iron. Iron can reduce in furnace at high temperature 600 to 700 using carbon as reducing agent. Similarly, aluminothermic process. Aluminum can is also very much stable and stable oxide and aluminum can use as reducing agent for some particular metal, that is chromium, iron, manganese, etc. And this process is called thermite process, aluminothermite process. And to extract chromium can be extracted in the presence of aluminum. This chromium oxide can be converted into chromium by reduction by the presence of this aluminum as a reducing agent. Similarly, this MnO2 can reduce to Mn in the presence of aluminum. This FeO2 can also convert into Fe, that is metal, in the presence of aluminum. Okay. Similar Ellingham diagram can also be constructed for sulfide ore. Thus, this Ellingham diagram is very much important in metallurgical process to predict different reducing agent and to predict the temperature at which that reduction can be done. Okay. That's all about Ellingham diagram. Thank you very much and have a good day.